Right. So today we have Mohammad Akhond tell us about mass deformations of long quivers in 3D and 5D. Take it away.
Okay, thanks, Julius. Thank you for coming to this talk. I know it's a bit unusual time for the Quiver meeting. So yeah, today I'm going to talk about mass deformations of long quiver theories in 3D and in 5D superconformal field theories. So this is the presentation today is based on these two papers, one which appeared earlier this week and one to appear next week. And this is in collaboration with Andrea Legramandi, Carlos Piñez, Leonardo Santilli, who's here, and Lucas, who's actually currently defending his thesis as we speak. Yeah, so the slides aren't changing. Okay, so my talk is a little bit technical in nature. So to make up for it, I'll show you a pretty picture here and there. And this picture is sort of a broad overview of what people do when they study superconformal field theories with 8 supercharges. So we're interested in these superconformal theories which have a life of their own in terms of operators and their correlation functions together with their possible deformations. And the most interesting cases typically, at least the ones that I talk about, they show up in the strongly coupled region of some gauge theories. So for that reason, it's usually difficult to have direct access to this information. Instead, we can probe this theory by using some effective field theory description and computing some RG invariant quantities. So the things in blue are things which are directly touched upon in this talk. In particular, I'll discuss supersymmetric partition functions, well, the sphere partition functions. And you can use this description to compute expectation values of protected operators. In particular, I'll talk about half BPS Wilson loops, circular Wilson loops. Okay, there is another useful perspective, which is usually, it's somehow a geometric description, which is coming from the realization of the superconformal field theories in terms of string theory, string theoretic construction. And usually the description here is geometric. Somehow I'm using a very broad notion of geometry. So this could refer to like geometric engineering or the holographic geometry. And there is connection to brane configurations in string theory. Okay, so let me now delve into what we're actually dealing with. So I mentioned effective field theory, and the effective field theory description that I'll be using in 3D and 5D is linear quiver gauge theory, depicted by this quiver diagram. So the formalism that we've developed is quite, well, the equations are quite similar in both 3D and 5D. So I'll use the same, well, similar notation, and a lot of the discussion will be in parallel. But this is kind of potentially dangerous because the physics is somewhat different. So I apologize for that in advance, but let's distinguish the setup. So whenever I talk about refer to a 5-dimensional superconformal field theory, what you should have in mind is that there's some UV interacting CFT, which admits a mass deformation whose low energy, this triggers an RG flow. And at low enough energies below some cutoff, it has an effective description in terms of a 5n equals 1 gauge theory whose Lagrangian is fixed by this quiver diagram. So in this case, the gauge groups will be SUN, and I'll set all the Chern-Simons levels to 0. On the other hand, when I talk about 3-dimensional superconformal field theories, you should have in mind some UV Lagrangian, which is again fixed by this quiver diagram. And this theory flows to some interacting superconformal field theory in the deep infrared, whose holographic dual I'm about to describe in a few slides. So in 3 dimensions, all the gauge groups will be UN instead of SUN, but I'll just use the same diagram, and I hope that won't cause any confusion. So I'm going to restrict throughout this talk to balanced quivers, which basically means that I'm enforcing this condition on the flavor ranks and the ranks of the gauge groups. But this is just a technical simplification. And what I mean by that is that you can relax this condition and you can still have superconformal field theory. This is not a physical restriction of superconformal invariance. This is just because I only know how to describe the theories of this class. I do not know how to relax this condition and write down the background. Okay, given this quiver diagram, you can immediately write down basically the key object in my discussion today, which is called the rank function. So the rank function is a different way to codify the same information that's contained in this quiver diagram. Namely, it's a function whose value evaluated at integer eta gives you the ranks of the gauge groups. So J is some integer going from 1 to p minus 1. And the rank function evaluated at integer values just gives you the ranks of the gauge groups. Okay? So it's the same, it's a different way of presenting the same information. And this is the thing that will be very key in my discussion. Okay, so this is the outline for the rest of my talk. So I've divided the talk into two parts. First, I'll discuss the supergravity. I'll quickly show you the background that we're dealing with. And there you will see the emergence of a 2D electrostatic problem, which is basically the consequence of the supergravity equations of motion. And I'll talk about basically the main work that we've done, which is generalizing this rank function setup to two rank functions. It will be clear what I mean, hopefully more. Then I'll discuss the holographic computation of expectation values of circular Wilson loops in antisymmetric representations, and as well as the sphere-free energy, what we call the holographic central charge. Then I'll move on to the matrix model side of the story, where I'll be able to give all the holographic calculations interpretations in terms of the dual gauge theory. So we'll define what's meant by the long quiver limit of the sphere partition function, both for 3-dimensional and 5-dimensional theory. And we'll see how the same electrostatic problem arises as now the consequence of the saddle point equations of the long quiver limit of the partition function. Here we'll be able to identify the interpretation of these two rank function setup as turning on a real mass parameter in the sphere partition function. And then I'll proceed to justify this, this interpretation by matching the Wilson loop expectation values as well as the free energy. Finally, I'll conclude by giving you some puzzles that arise from this study and also mention some potential future direction. Okay, so let's get started with the supergravity part of the talk. So I'm interested in holographic jewels of 5D superconformal field theory. So there's a maximal, the maximal bosonic subgroup of the 5D superconformal algebra is, well, basically there's a conformal group in 5 dimensions whose isometry is realized as an ADS factor in the metric. There's also an SU2R symmetry, which requires the presence of an S2. So I'm in type 2b, there's a 10-dimensional space-time. So 6 plus 2 is 8, which means there are 2 remaining directions, which I coordinatize by sigma and eta. So this solution will be describing some PQ5 brane webs. So there's in addition a dilaton, and there's also a profile for there are PQ branes, and there's also 7 branes. So there's a profile for the form fields. And as you can see, this is a kind of it's a warped geometry. So there are warp factors appearing in front of the various parts of the metric. And the functions f1 to f7, which appear in the background, they all depend on the 2 coordinates sigma and eta. And moreover, their dependence can be realized in terms of a potential, which I call W hat, together with its derivatives in sigma and eta. So I don't think it's particularly useful to give you the entire background, but just to give you an idea, for example, the function f1, which appears over here, takes this kind of form.
Mohammad?
Yes?
Are you using F4 at any point?
Am I using?
The algebra F4.
No, I'm not using it. I only realized the bosonic part.
I see.
I mean, yeah.
Yeah, so
I'm
it's
only
just
giving you the boson.
it's just a title that people give once in a while.
Yeah, it's true.
There's never any application. Okay.
Yeah.
Thanks. Okay.
Yeah, anyway, I'm just giving you some intuition. I'm not giving you the explicit background. I'm just giving you some intuition why it looks, trying to motivate why it looks like.
Antoine is speaking.
Sorry?
Okay. No,
He's
it's
not speaking. Let's continue.
I see. Okay, so thanks for the question. Right, so we've written this background. It's codified in terms of this what I call a potential. And moreover, so if you plug this into the type 2B equations of motion, this basically collapses into this one condition after massaging it a little bit, which is this equation is valid in the absence of sources, so away from brain. And this is where the electrostatic problem is coming into play. Okay? So this is a 2D Laplace equation. So in order to understand what this background, to compute anything in this background, I need to solve this differential equation. Okay, so let's go ahead and do that. Again, it's not moving. Okay, sorry, before I solve this differential equation, let me also very briefly mention the three-dimensional analogs. So here the conformal group is now SO2, 3, so there's an ADS4 factor in the metric. And our symmetry is now SO4, so there are two spheres. So geometry is a little bit different. And once again, this is a warped product. So this notation with the, it's not a Cartesian product. There's a warp factors depending on sigma and eta. And once again, everything is, all the dependence on sigma and eta is collected into a potential, which has to solve a Laplace problem in 2 dimensions. Okay, so given a background, you have to solve this differential equation and you have to specify boundary conditions. And the different boundary conditions that you impose on this field, on this potential, are basically giving you the different field theory duals, right? So you have a vast landscape of 3D and 5D superconformal field theories, and which particular field theory you're dealing with is basically the choice of boundary conditions you impose to solve this differential equation. So when you're close to sources, you have to, this equation is modified to a Poisson equation. So there's a delta function localized around sigma. And I'm going to impose boundary conditions that the potential vanishes at sigma equals 0 and, sorry, eta equals to 0 and eta equals to p. So you can think of the situation where I have two conducting planes, one at eta equals 0, one at eta equals to p. And there's a density of charges localized around sigma equals to 0, going from 0 to p. So this is the rank function, which I showed you before appearing here. So this is how this background knows about the quiver data, right? So it's hidden inside this rank function here. So now you can solve this by separation of variables. It's convenient to Fourier expand the rank function. And basically, now the problem is to find these Fourier coefficients, which you can find from, given a quiver, you can just plug into here and get the Fourier coefficients. And this, you feed it into here, and this gives you W, right? So given a quiver, you extract the rank function, you read off the Fourier coefficients, and you plug it into here, and that specifies the whole background for you. That's basically the message. So I realize there's a bit of information here, so maybe if somebody has a question. Okay, so in this work, what we wanted to do is to generalize this construction in the following way. I want to consider a situation where instead of having a single rank function, I have two rank functions, which I call R1 and R2. which are separated by some finite distance sigma 0. Okay. You can solve this differential equation again, and actually you, by linearity, the solution is just the sum of the other two, the individual solutions R1 and R2, where here the argument sigma is shifted by sigma 0. And now a natural question is, what exactly is going on in the dual field theory? Okay. And this is the question I want to answer in the remainder of this talk. Okay. Let me just mention that from the get-go, it should be, there are some hints. So when you go to the limit where sigma 0 is 0, you basically collapse these two rank functions on top of each other. And so the answer is basically a sum of two rank functions. So you have a quiver whose rank function is basically a sum of two rank functions. The non-trivial thing to understand is when sigma 0 is finite. So when you actually separate these two. You can get some hints to the answer to the question that I mentioned by analyzing the free energy. So holographically, you compute this as a kind of a weighted volume of the internal manifold, which is basically computing the effective Newton constant on the ADS part of the geometry. And the answer that you get is kind of interesting. So in both 5D and 3D, the coefficient here is different, the dependence on K is different. But what I want to highlight here is the dependence on the Fourier coefficients of the two rank functions. So in both cases, you have a part which depends only on the rank function on one rank function, and a part that depends on the other rank function, or the Fourier coefficient. And then you have a small interaction term, which is suppressed exponentially in sigma 0. Okay, so here I'm just summarizing the same thing. The holographic central charge, which is the object due to sphere free energy, as a function of R1 and R2, is factorizing to three pieces. So two pieces are just two rank functions not talking to each other, and then which is suppressed in sigma 0. In particular, the asymptotic behavior in sigma 0 is even cleaner. So when sigma 0 goes to 0, I just get the sum of the two rank functions. And when sigma 0 goes to infinity, I just get a factorization. Moreover, you can show that when the sigma 0 goes to 0 limit is strictly larger than the sigma 0 goes to infinity limit. And in addition, it's actually stationary at the 2 points. And moreover, it's also monotonic in sigma 0. So this is in the spirit of the S theorem, this is highly suggestive that this is triggering some RG flow. So turning on sigma 0 is corresponding to turning on some RG flow. Okay. That's the hint that I get from here. You can also compute expectation values of antisymmetric Wilson loops. So I think that maybe this expression is just only good enough for purpose of comparing with later computation in gauge theory. So I don't expect you to get much out of this. But let me try to highlight a few key things here. So here I'm turning on a Wilson loop at a certain gauge node. So remember, eta was a coordinate along the quiver. So here eta star is telling you the particular value, or is signifying the gauge node at which I turn on the Wilson loop. Okay. And sigma star is fixing the representation. So I'm considering the Lth rank antisymmetric representation of the whatever gauge node I turn on this Wilson loop at. And the representation is fixed by, well, sigma star is obtained by inverting this relation. So it's basically fixing the representation for you. And the other, other than the fact that you can match this from the gauge theory side, the other significance of this is that, again, it's hinting some factorization for you. So notice that there are two almost identical pieces. So one piece over here, which depends only on the quiver data of one quiver with one rank function. So this Fj is the flavor rank function of one quiver. And then there is another piece, which is almost identical, except that it's shifted in sigma 0, which is a deformation that I'm turning on. And it only knows about the quiver data of another quiver. Okay, let me come back to this in a moment, just because I want to show you a picture if the equations were a bit confusing. So in pictures, this analysis that I just sketched before your eyes is giving me the following suggestion. When sigma 0 goes to 0, I have a linear quiver, linear balanced quiver, whose color and flavor ranks are as follows. So at each node, I have N1 plus N1 tilde colors, F1 plus F1 tilde flavors, and so on. As I turn on this parameter sigma 0 and I go all the way to infinity, this quiver is factorizing to a direct sum of two CFTs, which are basically one of them is just depending on the ranks are N1, N2, so on, F1, F2, and the other one N1 tilde, N2 tilde, F1 tilde, F2 tilde. So I hope it's somewhat clear what is happening. Okay, so let me now come back to the previous slide, but let me say a few words. So I claimed that I have a superconformal field theory, which is somehow related to this quiver gauge theory. And I'm turning on a deformation, which I would like to interpret as triggering an RG flow. Okay. But the background that I showed you has an ADS factor stuck in it. And all the manipulations I'm doing solving this differential equation is taking place in a sigma eta plane, which is transverse to the ADS part of the geometry. But any kind of RG flow will break conformal invariance. So how can it be that I have a conformal ADS background for all parameters of sigma 0? So something should be going wrong. And indeed, something is going wrong. So here I'm showing you the plot of the things that the thickness of the background can show up in various places. But I'm just showing you a plot of the dilaton because it's one of the easiest, quickest ways to see that something is happening here. So I'm plotting, maybe the details are not too important. I'm plotting the profile of the dilaton for a situation where I'm fixing P to be 15, and I have two rank functions, which are triangular rank functions. So these are linear quiver with a single flavor group. So there is one of them has a flavor node at eta equals to 6. The other one has a flavor node at eta equals to 9. And if I evaluate the dilaton far above and far below in the eta direction, sorry, in the sigma direction, then I get some. I don't see any problems. But evaluating the dilaton in this range, where sigma is somehow between 0 and sigma 0, you see that the dilaton is becoming negative. Okay, so the fact that we're forcing this background to have an ADS factor in it is showing up somewhere else. So it's telling you that you do not have an ADS geometry. You do not have a reliable background in these intermediate ranges. But in the limits where sigma 0 goes to 0 or infinity, you recover your solution. Okay, so that was the end of the supergravity part of the talk. And I'm actually doing okay for time. So if there are questions, maybe I can answer some questions.
Yeah. What kind of physics can you extract from these negative values? So what really happens there to avoid this negative value? Is it flattened in some way? Or?
No, I don't. So the background is not reliable there. However, some quantities that you compute in this background, we were able to match them from a gauge theory computation. So even though the entire background is not valid, there are certain computations. So for example, this Wilson loop expectation value, it matches on the nose, as I'll show you with the matrix model calculation, for all values of sigma 0. Okay, so irrespective of.
You could push the solution beyond validity to in order to get
not the whole solution, but certain computations. So Carlos maybe has a better understanding of this. So Carlos has experience with this kind of backgrounds that have some singular behavior, and his well, I'm just going by what he's told me is that this kind of situation does occur in supergravity, and sometimes there are backgrounds which present singularities, yet there are particular quantities that you can compute which do not, which are independent of the singularity. So this particular behavior is arising due to one particular factor in the metric, which we call lambda. And there are certain computations where cancellations happen, and this lambda, which is the problematic piece, drops out of the computation.
Okay.
So the expectation value of the Wilson loop is an example of that. Also, the free energy calculation has this kind of cancellation. So
yeah, many times for us we take too many 8 branes in local model, but and the numbers are small, they are not large. So numbers are small, and then you get to a case where it forces the dilaton to be negative at some point. We ignore those things, and at least to get the magnetic quiver, you get nice results. From there you can continue. So that's just from, you know, relying on this. You say, okay, I'm not going to care, and I'm going to derive magnetic quiver, and then it seems to give reasonable results. So it seems like you have, there's a whole range of functions where this would happen. I'm just wondering what is the scope of those things. Maybe a question to Hans.
Yeah, I'm not sure. In this background, at least as far as I know, there's only 2 quantities, which is the free energy and the Wilson loops.
I see. Mm-hmm. Okay.
Yeah.
Thank you.
Yeah, I'm not sure if there's some connection between this kind of computation and the magnetic quiver thing that you're mentioning.
Mm-hmm.
I think this was just a comparison that if you have like some bad behavior for the dilaton, you could just not care because you're trying to extract something else. And anyway, you're doing
but in the magnetic quiver thing that Ami is mentioning, though, at least in the examples that I know, you can always just add enough oriental fold planes by hand away from the part which you're trying to extract the magnetic quiver from.
Anyway, maybe we can discuss this later.
But orientable quivers are not a choice. You cannot add them wherever you want. These are very specific backgrounds.
I'm saying you can add O8 planes infinitely far away in such a way that doesn't talk to the rest of the brain system that you're extracting the magnetic quiver from.
Well, the problem will happen. The problem will happen at finite values, not far away. The dilaton is going to have a negative slope, and at some point it will just go below 0.
Let's discuss this afterwards, because I think this is completely orthogonal to what Mohammed wants to tell us. But,
I had a question regarding your plots before. So do you impose boundary conditions on the at p equals 0 and 15 for your function here, or is it?
Yeah, so the boundary condition.
Because they are not all the same. That's why I'm asking. Oh, is it just flat? Ah, yeah, it's a Neumann condition. The slope should be flat.
Yeah, I think it asymptotes basically to it's flat.
Because I guess this is crucial to know whether really you have these negative values. Like the boundary condition should be the thing that fixes. So how do you do that?
I don't know. I'm not sure if I understand you correctly for the boundary conditions, but the boundary condition that we impose, maybe I gave it here. So the boundary condition is that at eta equals to 0 and eta equals to p, this potential goes to 0.
Okay, so you impose this, and then you have a way to relate this function f something, the thing that was giving the dilaton. And I'm just surprised that the boundary conditions are not the same for all these functions, but maybe it's.
Yeah, so here the value of sigma. So these are plotted. I see. I understand what you say. So these are for different values of sigma. So these are all for different values of sigma.
Yeah, so in your rectangle,
sigma is appearing in here. So the dependence is not only on W hat. So I give the same boundary conditions for W hat, but I'm not fixing the value of sigma. The value of sigma is different.
Sure. So in your drawing, you have one curve for each value of sigma like this, and the eta equals 0 and eta equals your maximum value. This is where you should impose some boundary conditions. These electric planes. But okay, I guess it's flat. Like on the drawing, it looks like it's flat. So maybe that's what you impose. Okay. Anyway.
Okay. Anyway, thank you for the questions and the discussion. So yeah, let me discuss the matrix model side of the story. So I want to well, to foresee where this is going, I would like to claim that turning on this parameter sigma 0 corresponds to turning on a mass, a real mass in the sphere partition function, where the mass is related to this sigma 0 in a way that I'll specify. Okay. So in order to do that, it's convenient to first do some reparameterization. So I'm going to introduce a new coordinate z, which takes values between 0 and 1. So I'm normalizing eta by the length of the quiver. And I'll introduce this rescaled rank function, which is basically dividing the ordinary rank function by n. This has the virtue that now all the gauge groups scale with n. Okay. Similarly, the flavor rank functions can also be defined. So this basically is coming from the this is a continuous version of the balancing condition, if you like. And the flavor ranks will also scale with n. And this is convenient because later on I want to take a single parameter n to be large, and doing this, the whole all the color groups and all the flavor groups will scale in a similar manner. Okay, so the sphere partition function has the following form. So in 5 dimensions, here the discussion is probably a little bit more about 5 dimensions, but the 3-dimensional story is very similar. There is I'm collecting all the one loop determinants and the classical parts from the Yang-Mills and Chern-Simons into what I call the effective action. And the instanton contribution is contained here. I'm interested in taking what we call the long quiver limit, which is taking this integer n, which was introduced by hand, and also the length of the quiver to be large. In this limit, the instanton contribution is suppressed. So I just need to worry about this factor. And moreover, in the long quiver limit, the integral is approximated by, well, it's dominated by the saddle point equation. So to leading ordering in the long quiver limit, I just need to evaluate the saddle point equation of this effective action. Okay, so you can turn on flavors for the turn on masses for the flavor groups. And you can do it for arbitrary number of families, but here I'm going to split them into 2 flavors. So at each gauge node, I'm taking F1 plus F1 tilde or Fj plus Fj tilde flavors, and I'm giving 0 mass to the first family, and I'm giving a mass m to Fj tilde flavors. Okay, so I'm doing a mass splitting in the flavor groups. In the effective action, this has the effect of shifting the eigenvalue of the special function that appears in the integrand by m. So this is where the mass is entering. And the effective action has this factorized structure again. So there's one part which depends only on the quiver data of one quiver, another one that depends on the other quiver, and then there's a small interaction. Okay. To find the saddle points of the effective action, I need to minimize with respect to the eigenvalue densities, which I haven't really discussed what it is. But okay, so in the long quiver limit, you just introduce eigenvalue densities, And so this is giving you the distribution of the eigenvalues, like the Coulomb branch webs along the quiver and in color space. So Z is basically now the coordinates along the quiver, and X is like in your eigenvalue space, in the color space. So the fact that I have two eigenvalue densities is coming from the fact that after I give different masses to different sets of flavors, at the same time, I'll take the Coulomb branch webs of N1, the first N1 colors, and I shift them in the opposite direction. That I shift that I turn on the masses in the flavor groups. So this is where the splitting into two rank functions, if you like, is coming from in the matrix model side. So now I have to minimize with respect to row 1 and row 2, which gives me two equations, but actually the two equations are related by a shift of x to x plus m. So I'm just quoting one of the equations here. And if you, well, this equation is already quite similar to the supergravity equations that we wrote down. So this is like a Poisson equation. There is one rank function localized around x equals 0, and then there's another one localized around x equals to m. And you can actually make this correspondence more precise, and comparing the two equations, you can extract this kind of map. So this was just by construction, the definition that we use for Z, which is eta over p, and the other just comes out of comparing the two differential equations. So the eigenvalue density that I used, or unscaled version of it, is related to the second derivative of the potential, which appears in the supergravity background with respect to eta, and the mass is related to sigma 0 by division by 2p. Okay, we can compute expectation values of antisymmetric Wilson loops, circular Wilson loops in this theory, with the mass deformations turned on, and this just corresponds to inserting this this factor into the inside the sphere partition function, and moreover, this well, we can already see that this is kind of linear in sigma, so this does not modify the Salopon equation. So its contribution to the Salopon equation is subleading in the long quiver limit. So to evaluate this expectation value, you just have to evaluate this expression on the saddle point solution to the differential equation. Okay, but actually it's the same solution as the supergravity, since it's the same differential equation. So you just plug in the solution that I showed you before, and you evaluate this expression, and you get a match on the nose with again with the supergravity expression that I showed you. So here now I'm using a bit more compact notation. So before we had two pieces, but now I'm considering the case where I have S families instead of two families. And each part will only depend on the quiver data of one of the factorized pieces. And there's also a shift by the mass parameter. Okay, then we can move on to matching the free energy. And the free energy is proportional up to some proportionality factors to the effective action evaluated on shell. So here I'd like to remind you of the schematic form of the central charge computation of the holographic central charge computation that I just quickly flashed before your eyes. So remember that there was a part that depended only on one rank function and another one that depended on the other one, and there was a small interaction which was suppressed in the separation between the two rank functions. Okay, we already saw some similarities between this kind of structure and the effective action. So there was a piece that, well, there were the factorized pieces and there was an interaction part. Evaluating S1 and S2 on shell immediately gives you a match up to some proportionality constant. with the supergravity calculation. Matching the interaction energy was actually a little bit of work. It's probably the most technical aspect of our paper. So I'm not going to be able to do it justice here, but very briefly, let me just mention that in order to get this to match, we have to remove the contribution of massive fields by basically subtraction. So when you turn on this real mass deformation, typically things are not clean. What the sphere partition function tells you is basically you see that some fields become heavy and some fields become massless, but the integrating out is not automatic. So you have to do this integrating out by hand. So since I want to match with the supergravity background, I want to extract the part which is just the interacting conformal field theory, and I want to throw away the massive field contribution. So in particular, I have to remove by hand, by subtraction, the contribution from the W bosons, which become heavy, as well as massive fundamental and bifundamental fields. Okay, so in 3D, this match is perfect after this procedure that we kind of had to invent to match this calculation. In 5D, the match is up to a Chern-Simons contact term in the flavor fugacities, which probably we need to understand better. But in the end, this is what we get. Okay, so I think I'm coming to the end of my talk. So let me just summarize. So what I did is I showed you the holographic duals to 3D and 5D superconformal field theories with 8 supercharges. And I mentioned that there is a 2D electrostatic problem that arises as a consequence of the supergravity equation. And the solution required choice of boundary conditions, which in the other hand gives me the particular field theory that I'm dealing with. And we also use the supergravity description to compute the free energy and the expectation values of antisymmetric Wilson loops. Then I showed you that the same electrostatic problem can show up as the consequence of the saddle point equations of the sphere partition function with masses turned on for the various flavors. And we match the Wilson loop and free energy. The Wilson loop match is straightforward, but the free energy needed some removal of massive fields. So let me just tell you a little bit about potential future things to come. So it would be very interesting to come up with further tests of our procedure for removing the contribution of massive fields. So I mean, I think we're quite confident that this is the right thing, but since this is the first time, it would be nice to come up with other similar situations and maybe other observables that can be checked. In 5 dimensions, I think we probably need a better understanding of the Chern-Simons contact terms of in the flavor fugacities. For example, is it possible to reproduce this kind of contact terms from the ADS6? So in the field theory, the half integer part of the Chern-Simons contact term is quite important, and it tells you physical information. So it would be nice to see if we can reproduce this from the ADS side. So the backgrounds that I mentioned have analogs there are analogous solutions which are dual to 2D and 4D theories with 8 supercharges. The supergravity side of the story almost immediately generalizes to these situations. It would be interesting to explore what the field theory implications are, or it would be interesting to study. Another thing which I personally think is interesting is that so we did a lot of computations with Wilson loop expectation values, both from field theory and from gravity. But in 3D, there's a very interesting story of mirror symmetry and vortex loops. I think it would be interesting to try and investigate that. It's also very interesting to extend this discussion to unbalanced quivers, so relaxing the balancing condition. And finally, I think probably the most important message of this talk is that this 2D electrostatic setup is very general, and you can just play around with various boundary conditions, and anything that you can basically solve should, in principle, have an interpretation in field theory. So it would be interesting to come up with more general electrostatic situations, for example, rank functions at intersections or rank functions at angles. That would be useful in extending the ADS-CFT dictionary. So I think that's all I have to say. And thank you for your attention.
All right, let's thank Mohammad. Questions? So maybe I can start with when you say unbalanced quivers, there the behavior in 3D and in 5D is quite different. Well, in 3D you can do anything with the balance, that's all fine. But in 5D, of course, you know that we want the low numbers of flavors. And how do you see this? How would you find such a condition from like what you're doing?
On supergravity.
So in the supergravity, this gives you the same bounds, basically. Is this what you're saying?
The supergravity doesn't give me any bounds.
Okay. So how would you see, how would you see that something goes wrong if I give you a massively overbalanced quiver in 5D? Or would you not see anything go wrong?
Yeah, so one possibility is to have rank functions, which we call them rank functions with offsets.
Mm-hmm.
So this will be a rank function that doesn't start from 0, right? So let me say it here.
I guess I'm more interested in the balance function, or the I don't know, the f, if you make f to a continuous thing.
I don't understand. Can you tell me again?
Okay, so you were talking about unbalanced quivers. So here, maybe I'm confused, but so basically they're the n's and then they're the f's. And making n to a continuous function is your rank function. And let's say we fix this, but now I want an f function. Like the fj.
Yeah, so
but now here to have some high number, like maybe you don't do it, but like just if we have a high flavor, then we know that there are no SCFT points at some point, or we don't see them at least. So do you find a problem in what you're doing?
Yeah, I mean, I don't know how to solve
maybe also this is in the outlook, so I shouldn't ask you at this point.
No, it's a very interesting question, actually, what you're asking. So the point is the following.
Yeah.
From the gauge theory side, it's quite reasonable to think that unbalancing corresponds to inserting some additional planes here, okay?
Mm-hmm.
So this is a computation that was done by Ullmann, okay?
Mm-hmm.
But yeah, I don't know how to solve this. Yeah, I wasn't able to solve this in the supergravity. So let me say that way.
Because it looks like you're doing a kind of 3D and 5D at the same time. Well, in many ways. And so then if you have an unbalanced thing, then in 3D, everything should basically go through. If you have a high, a positive balance, high positive balance, but in 5D you should have, so that's my question. But okay, fair enough. Do we have more questions?
Yeah, okay. This kind of unbalancing is going to increase rather than decrease flavors, but yeah.
Yeah, exactly, and that would be in 5G problematic. But okay, more questions. So also so another thing, back to what Ami was saying. Well, you showed us the negative dilaton, and so just to see if I understood correctly what you were saying, is that we have here some supergravity solution. It's some approximation, and it's actually not a good approximation, but you can it's still good enough to get some Like it computes some things correctly and some things it gets wrong. Is that the statement?
So there will be singularities in the metric, for example.
Mm-hmm.
So that's already a problem. But the particular calculations that work means that it matches with the gauge theory side.
Okay.
So that's the meaning of this word. So I can compute something even though the background is singular, and somehow it matches. So yeah. That's the meaning.
What's the problem with the background being singular?
I mean, you have a metric that has a singularity. It's kind of a naked singularity also because there's no horizon to
Okay,
to hide this.
fair enough. Are there more questions?
Yeah.
Okay.
If you like another, so if you want to, for example, compute certain volumes, there will be divergence. This is another signal of the singularity.
I see. Okay, so if there are no questions now, let's thank Mohammad again. We'll stop the recording.